Hello, my name is Georgios Siropoulos. I'm the Chassis Dynamics Manager at Automobili Pininfarina. And today we will be presenting with Marco torque vectoring methodology developed in synergy with driving simulator from a VI grade. Automobili Pininfarina has been working with Danisi engineering to develop new chassis concepts with the use of an integrated method. That entails the use of offline simulation and analysis and, of course, in-the-loop tools in order to further enhance the quality of the result. I will be making a short speech here in order to make like an introduction, if you like, about how we as Automobili Pininfarina view this process with the simulator. And of course, I will leave some of the more in-depth talk to Marco. One of the most interesting tools we have been using so far with Danisi engineering is the driver in motion simulator from VI grade. That is an amazing tool so far that has enabled us to the opportunity to evaluate not only suspension architectures and chassis setups, but also various different active system configurations and integrations with the car. From the customer perspective, this has been a great value to us for many reasons, as you can imagine. Many people mentioned already things like reducing the time and costs for prototype parts and proving ground usages that we all know how expensive they are these days and how much they can impact budget. Of course, the ability to make very quick setup changes on a vehicle model level, and sometimes even on the fly. I was very pleasantly surprised to be able to sit inside the cabin and talk to the guys and change something on the fly and evaluate it. Of course, something very important from past experience, not having to deal with issues typically found on early prototype cars that significantly can slow down development. And we all know we're talking about things like charging and firmware issues and et cetera, et cetera. And then we have issues like finding and rectifying performance deficiencies and make sure we deploy strategies in order to mitigate issues like this and arrive at the testing grounds with a solution that is much closer to desired. Of course, last but not least, very importantly, it's the driving simulator has allowed us to expose people from the company that they are less specialist drivers or evaluators to various concepts and show them back to back with differences with either benchmark cars or other reference vehicles. One of the systems, of course, that has been reviewed a lot for Automobili Pininfarina cars is the torque vectoring through independent electric motors. As we all know, such systems can be very complicated to tune and integrate with other systems like stability control and traction controls and other active or adaptive technologies. And they do require a very deep study, both from objective but also from subjective point of view. Typical example is that the steering feel, for example, can be heavily impacted, especially when the torque vectoring is present at the front axle. And I know Marco will expand a lot more into this. Therefore, suspension and steering geometry require some level of adaptation from a design perspective in order to accept the application of torque vectoring. The methodology presented today will demonstrate the route followed for defining some of the performance targets while integrating them into the design and development loop with the use of offline tools. Then these targets, of course, have been and will be further characterized subjectively on the simulator in order to better understand the results and the trends that we should be following in real-life development of the car when we actually arrive at the proving ground and whenever we want to make changes that we want to implement. At this point, I think it would be appropriate to welcome Marco Fainello, CTO of Danisi Engineering, that will talk you through some of this methodology. Thank you.
Thank you, Georgios. So we are going to see how we develop this methodology to make it an effective tool in order to develop a car. It's a methodology that at Danisi Engineering we have developed through many years, I would have to say many decades, because we started our first experience in the early 90s. And it is designed in order to give applicable, effective indication to the people who needed to design a vehicle. Just a brief overview in order to show you what are the main principles that we are applying for this development. we see here that we base our target parameters to some analysis that we do, define the mission and the profile of the car, also including the comparison with the benchmark that could be physical or virtual. These parameters are including handling, soft handling, hard handling behavior, steering feeling qualities, and when it is appropriate, but it is only partially the case for this application or for NVH, including different conditions of driving, different drivers, and different parameters. You see here a video of our static simulator integrated with what we call HILDIS, hardware-in-the-loop dynamic steering system, which we saw also in some previous presentations from other companies. It is a rig that we have developed internally in Danisi engineering with the support of the related company Meccanica 42, that is able to apply to each wheel a load on the rear axis of the suspension of a real car, in order to provide the right loads through the steering systems and up to the wheel steering. So the driver can feel subjectively the correct behavior of the car on the steering torque, and we can rely not only on objective parameters but also on subjective parameters to understand where we are in development and how to integrate the system. It is used for different systems, including ADAS and suspension design. In this case, we of course use for understanding how to optimize the suspension design and the torque vectoring controls. Even though the chassis is physically present, it is not necessary that the chassis is actually the real one of the car we're going to develop, because through an integrated approach, through the use of software in the loop, we can parameterize some of the aspects, also the physical parts, in order to take into account what would happen, for instance, if we change the trail, the arms, the kimbing of the suspension, or even other physical parameters. As you know, the suspensions are traditionally designed with some specific tools and approaches that normally do not take completely into account the controls that are going to be applied to the same axis in suspension later on. This means that normally the suspension are designed, if you need to design a suspension for torque vectoring application, especially for the front, there will be an attention in order to keep under control some parameters and to limit as much as possible the influence of the torque applied to the wheel to the angle that are affected to the suspension or to the wheel in the car, and to the effect on the steering wheel torque in the case we are talking about the front axis. What we can do here instead with our approach, which I'm going to show here, we take a different point of view. Instead of designing a suspension in a way and designing a control in a separate way in order to achieve certain results, we start from what the result that we wanted to achieve. So you see on top that we have some vehicle targets that are developed and agreed based on customer, on client requirements, and are normally verified already from the beginning using, as I said, benchmarking on real car, but with an extensive use of virtual benchmarking on simulator, in order to make sure that all the target, all the attributes that we are going to define as goal for the car that we want to design are meeting the expectation of the clients, including the subjective feeling, and that are possible to be achieved with the technology that are used for designing and producing the car. From this target, on one side, you see on the left of the slide, we start a first initial design of the suspensions, from which we derive models that at the beginning is a multi-body model that is meeting a first definition of the attribute of the suspension that we need to achieve in order to match the vehicle target that we had defined before, and in order to be compliant with the constraint of the suspension design. That could be not only coming from handling, but from packaging, from comfort, from cooling system device integration in the car and in the chassis. From multi-body analysis, we can perform some simulation based basically on a virtual KNC in order to understand how the suspension will behave and make a first optimization of the suspension behavior in the constraints that we have defined in the project. And from the KNC, we can then define, from the KNC analysis in multi-body and the first offline simulation, we can create a virtual car real-time simulation model that is again used offline before we really get into the simulator. Offline, we can use some optimization without the human in the loop in order to meet all the objective parameter attributes that are defined in the process, and start the simulation with the human in the loop already from a very good point of view of parameter optimization. Then we move to simulator. We use in this process for this kind of project, like we did already for other projects with the similar mechanical and control integrations, we use static and dynamic simulator. First, on the static simulator, we are checking that everything is matching and the first objective feeling from the driver according to the torque steering that he can feel. And we can start with the first parameterization of some parameters, exploiting the fact that at the static simulator, we do have one physical hardware in the loop mounted on the simulator. From this analysis, we are able first to identify which are going to be the real behavior, the real feedback of the steering system, and identify the steering system that can run on a dynamic simulator, and check that all the software and hardware in the loop are working properly and properly matched with the human in the loop. The simulation is normally organized in this way. We have basically two approaches. The one on the left is a sort of standard approach where we put hardware in the loop in the system, in the VI grade hardware provided by concurrent computing. And all the software in the loop is compiled in a Linux RT simulation system to be part of the whole model. One other option that we use more and more often, because it offers some flexibility and interesting performance, is a co-simulation, where the part of the software in the loop is compiled for different targets, for different systems. That could be ECU, it could be fast prototyping hardware, it could be Windows computer, depending on opportunities and on the different systems. And then the co-simulation of this software in the loop runs in real time in co-simulation, as said, with the simulator and with the hardware in the loop through an Ethernet communication, as it is indicated in the line. Very often we use both approaches at the same time together with the standard hardware in the loop. And this is more or less the first result that we achieve from this integration. We see here mainly the offline results, where we could evaluate the effect of different parameters. In this case, just to give you an overview, we just highlighted the effect of having torque vectoring on or and off, and torque vectoring with two different setups. We can have a steady state behavior like the top two graphs and the bottom left graph. We can analyze the transient behavior like in the bottom right graph, and we can analyze many other parameters, first in an offline simulation with objective parameters, and then repeat with online simulation with human in the loop in order to integrate the subjective evaluation. From this part, we can have a full, sorry, I go back once, a full loop that allows us to have tools to design controls, control tuning, and suspension at the same time. So even before we really start designing the final definition of the suspension, and we really freeze the control in the car, we already know which are the best compromise between mechanical and controls parameters in order to achieve in the best possible way the target, the performance target that we have already identified in the first stage. Not only we do this at a very early stage, so when we can still make a lot of choices without affecting time and cost of the final project, but we also apply this phase without and with human in the loop to anticipate part of the failure mode analysis. We have seen that if we can simulate some situation where some sensor, actuators or system have an anomaly behavior, have an error, are not working properly, we can already anticipate at this stage what kind of strategies apply and study if, for instance, we need a hardware redundancy in some part of the sensor actuation or control system, or if we can evaluate different approaches in order to get a good behavior of the system, even in emergency condition, without affecting the project by adding external additive components. We can also make comparison of different components, because in this simulation, we also simulated the real behavior of sensor, hardware, and actuators in order to make sure that all the settings that we do are representative and validated. This is, in few words, the general overview of the methodology that we apply for suspension design, mainly front suspension design to torque vectoring for the Automobili Pininfarina Battista car. And this is just one part of the methodology that we are using, which are following more or less pretty much the same principle, and that we apply to the whole design of the car, to the different projects where we are involved. As you can see, starts from the benchmark, starting from a real benchmark on the track and indoor and outdoor test, in order to create through one proprietary method the virtual benchmark of the car. So you can easily understand how a virtual benchmark of existing car is useful, because we can mix different solutions and transform the comparison into the project that we want to and the product that we want to create. We do a loop, which is the loop you see on the left, in order to converge to what are the target of performance that we want to achieve, and what are the technology that we need to use to achieve this target. And at the end of this loop, we converge to agreed target to be achieved. We already have automatically what in the graph is called subsystem functional specification. The overall target of the car or the vehicle are transformed in system specification of the single subsystem: suspension, steering, chassis, weight distribution, wheelbase, and other things, including the controls that we need to have in the car, including what kind of speed rate, what kind of latency, what kind of error in the sensor we can accept. From this point of view, we know how to design the car, and we designed the first prototype already knowing that if we are able to match the subsystem functional specification, the first prototype will behave exactly as expected from the beginning for the performance that we have identified. In this case, for this project, it was handling and steering feeling. Then we start with the first prototype already in a condition where the behavior of the vehicle is already optimized, and it's very close to what we want to achieve at the end. And so we can save a lot of time and money in order to do only the final tuning and all the reliability check at the track in order to complete the project. It is an overview of the approach that we have developed through the years and that we have applied to this car. And I leave now the words to Georgios to draw the conclusion and the final considerations.
Thank you, Marco. Of course, as you most appreciate, subjective driver feel is paramount for Automobili Pininfarina cars, not only for the Battista, but any future products. It's very important to make sure we shape our vehicle dynamics DNA, and we offer engaging cars that are safe to drive and ride well, of course. The truth is that we probably do not need the driving simulator to tell us how powerful a torque vectoring system is in its influence in vehicle dynamics behavior. This can be easily extracted from offline simulations, quasi-static and transient events. They can easily demonstrate that with a few graphs. However, as we all know, it's not always about the numbers. Experience has shown that sometimes something that might look right or good on paper or on the screen, it can be translated to a subjective driver feel that can be either undesirable from the confidence perspective or the drivability perspective, or simply not being fun enough. The benefit with the Danisi approach that Marco has presented is that the simulator offers us the extension on vehicle dynamics for that exactly aspect. It allows the development driver to go through a plethora of different scenarios and setups and investigate which of those that have been characterized also objectively and offline are worth exploring in real life, and take it to the next level where we prepare the car for the proving ground and the racetrack. The development process, as you can imagine, is very similar to the real life scenarios. Tested configurations can be prepared beforehand, but also various parameters can be changed on the fly, enabling the evaluator and the development engineer to experience different configurations back to back without losing reference. Finally, and as a conclusion, torque vectoring systems with electric powertrains can offer a very substantial enhancement to vehicle dynamics. The effective implementation of such systems requires a synergy with suspension, steering design, including a lot of iterations between those and ultimately linking the subjective feel into the loop. This is often a process that is very complicated and requires a structured approach in order to make sure that everything works in a homogeneous manner. And that's exactly what the methodology from Danisi Engineering is achieving. And as was presented today, it has offered the opportunity to Automobili Pininfarina to explore chassis design configurations incorporating complicated systems such as torque vectoring that ultimately help us reduce design time, development costs, delays, while achieving high quality vehicle dynamics from any aspect, and particularly the driver's feel, which, as we know, is a very essential element for making a car feel special, drive special, and be unique in the market. Thank you for your time, and I would like to thank Danisi Engineering and VI Grade for this opportunity.